Okay, welcome back to this part 2. We left our problem after finding this voltage in the S domain, and now what we're going to do is to use what we have defined here. So we're going to recycle this circuit and write the equation now in terms of, whoops, what happened here? We're going to write down the equations in terms of V, right? So copy paste here. So we're going to say now coming back to our circuit and equations, right? So we already defined the equations essentially, right? So the difference now is that we're gonna write them down in terms of that voltage V. That's the only difference. So actually we're gonna copy paste here, and we're gonna say, okay, where is V here? Since these are KVL, some of this voltage are gonna be actually those V. So if we go back to our definitions, we should see that this voltage, it's gonna be given by, actually let me write down the equations one more time, otherwise it's gonna be not pretty. So let's write down the equations. 2 over s plus 1 minus 2 over s times I1, no surprise, minus V. That would be the KVL related to that I1 that we wrote down there. Second one, it's going to be voltage, right? This voltage here minus the voltage drop at the capacitor here. So here we're going to have I2 minus I3 minus the source, 4 over s equals 0. And KVL 3 should be, in this case, what we can do to avoid putting more I2 and I3, it's to take this loop. That is going to be easier, right? Because we have V, we have the source, and I3 is going to be the only unknown variable. So we can do that. Let's call it KVL 3 comma, right? Which is not the same one that we defined previously, but we're going to have V minus 1 times I3 minus 4 over s equals 0. So again, now the key is that we have V. It's a very big expression, but we have it, and we can use all our knowledge in algebra to get to expressions for I1 and I2 and I3. So then by algebraic manipulation, we can find I1, I2, and I3, right? So I'm gonna leave this part to you. Train this. This is gonna be extremely important for all your homework problems, lab work, and also midterm or final exam. So you're gonna get to an expression. I have triple checked this, so you should definitely get to this expression here. So I'm gonna do it in 2 steps such that you can check in the middle. Calculations, 2 over s plus 1 minus V. V is what we found up there. So the most compact way is going to be 3s squared plus 10s plus 12 over 2 over 3s plus 4 times s plus 1. Okay, So I'm giving you a little more detail than just a solution. I'm giving you an intermediate step so you can check your progress. V minus 4 over S plus 2S I3. So what is I3? I3, according to this, is essentially V minus 4S. So V3, I3, it's minus 3S squared plus 10S plus 4 over S over 3S plus 4 times S plus 1. So if we plug I3 in here, you should get to minus, this is the most complicated one, I think, S plus 2, 3S squared plus 10S plus 4 over 2S over 3S plus 4 times S plus 1. Okay, those are the currents in the S domain. Unfortunately for you, the solution is asking for currents in time. So now we need to take the inverse Laplace. And I can guarantee you that there's no table that is going to give you exactly this answer. So you need to work your way out of here. The way to do it, I'm going to show it to you only for I1. Okay, only for I1, and I encourage you to do the same procedure for I2 and I3. So to take the inverse, we need to use what we call partial fractions. Partial fraction decomposition. So probably I'm gonna walk you back to the calculus time where you had to do this at some point. So let me show you the approach, which is the most important thing. Don't try to memorize formulas because you're gonna forget about them. But the approach is the most important thing, because that it's gonna stick in your head, and most probably you're gonna forget it, but then you're gonna remember the key words or the main concept behind it, and it's gonna be fresh again. So the idea here is that we want to decompose this fraction into sum of individual terms. So based on the rules of partial decomposition, in this case we're going to have a constant element related to this constant value, right, or this constant value, plus some b divided by the second value that we have here on the denominator, right? So over 3s plus 4 plus another value over s plus 1. So that's the key. The key is, okay, how we can decompose this thing in individual terms. Why this individual terms? Because we know the Laplace inverse of a constant value. We know the Laplace inverse of this simple, let's say, fraction, a number divided by something with a pole that is negative. That in our mind, we know that it's going to come back to a exponential with a negative sign, right? Same here. So the point of all this is that you can actually put this together. I'm going to do it like this, right? 3s plus 4. So you can combine those things, and you can equal the numerators. So we can put a 2 here. That would be fine. And the numerator in this case would be to make it a, to make it equal to that, 2a times 3s plus 4 times s plus 1 plus b times s plus 1 plus c times 3s plus 4, right? I'm not sure about this 2. We can cancel them out. Okay, never mind. So that's the key. We're going to have some numerator that is going to be a function of a, b, and c. And the idea is that we're going to equal the part that it goes with s squared, with that 3. We're going to equal the part that goes with s, with this one. And we're going to equal the part that is constant with this one. So we're going to have functions of a, b, c, 3 functions related to a, b, c, and 3 equations, right? So we can solve that for a, b, c, and you can find what are the constants that allow us to decompose this fraction into 3 individual terms. That's the whole key. So after solving for ABC, we get, what do we get? That I1 can be decomposed as minus 1 over 2. That means that A, it's minus 1 over 2. B, it's actually 6, so 3s plus 4. And C is 5 over 2, so minus 5 over 2 over s plus 1. How do we know that our answer is correct? Because you can combine them back, right? You can combine them back. We have a denominator, a common denominator, 3s plus 4, s plus 1. We have something on the numerator, and that result, this whole put back together the original fraction, should be equal to this one. That's a way for you to verify that the partial decomposition was correct. Okay. We have that, and finally, now we take, let's use another color, inverse Laplace. So Laplace inverse. So each term is going to have one specific value. So this one is 1 minus, what did I do? Minus 1 over 2 delta of t. This one gets simplified, so you're going to get, you can divide everything by 3 here. So you're going to have 6 divided by 3. And here we're going to have s divided plus 4 over 3, right? So if we do that, we should get 2 exponential of minus 4t over 3. And this guy here should become minus 5 over 2 exponential of minus t. So that means that I1 of t, it's going to be exactly the sum of each component, right? This is a linear transformation, so we can take the sum of its components. 4t over 3 minus 5 over 2 exponential of minus t. And this is valid for t greater than 0 because everything is defined for the step function. Okay, and you can check your results. So let's say similarly, I2 of s should be, let me check my calculations here. Sorry, I2 of t should be exponential of minus 4t divided by 3 minus 3 over 2 exponential of minus t minus 1 over 2 delta of t minus 1 for t greater or equal to 0. And finally, I3 of t is going to be 3 exponential of minus 4t over 3 minus 3 minus t minus 1 and t greater or equal to 0. So how do we get the solutions? Doing the same procedure. Taking this expression in the Laplace domain, applying partial decompositions, and then using the tables for the Laplace transformations for each individual component. So we can get each individual component of the entire signal. Okay, that's my recommendation. This is a very good exercise. I know it's just one, but it touches all the main points related to calculations using Laplace. So quick recap: you always want to move your circuit into the Laplace domain. You can define the equations. I mean, this is a square set of equations, three unknowns. We can solve it. We can definitely solve it. However, it's kind of difficult when everything depends on S. It's not that we're going to find a value for I1, I2, and I3. We're going to find an expression in terms of S. So what we did on part C was essentially take this step by step. So moving through these elements such that we can calculate this internal variable that we defined that was useful at V, that allowed us to calculate I1, I2, and I3. Once we do that and we get an expression in terms of S, then 99% of the cases you can do partial fractions and divide that very complicated fraction into individual terms that can be applied in terms of the inverse Laplace to get your time domain components. That's a whole procedure. I hope it's helpful. Re-review it. Check your solution based on what I've showed you, and I hope you get your results right. Otherwise, feel free to reach out to us. Thank you.